Hi, everyone, and welcome to Swagelok's webinar on hydrogen fluid system design. We're going to wait just another minute or two for folks to join, so please give us one more second and we'll be right back. Hi, everyone. Thank you for joining Swagelok's webinar on hydrogen fluid system design. I'm Craig Gifford. I'll be your moderator today. Today's webinar is going to talk about why hydrogen designs are different compared to oil and gas designs. And so, as we all know, many fluid system designers are tackling the difficult task of handling hydrogen for the first time. And so engineers are kind of finding out that hydrogen systems require a different design parameter than those just transferring in from oil and gas. So it takes a little bit, there's a little bit of a difference. And so today, for the next hour, Chuck Hayes, who is Swagelok's global technical lead for clean energy, is going to walk us through some of the things like fundamentals of why hydrogen is hard to contain, the differences between hydrogen and oil and gas systems, the importance of using small bore tubing versus piping, and some other considerations for hydrogen system valve and fitting selections that you should probably be aware of. So just a little bit of housekeeping as we go today. We'll be able to take some questions at the end. You can put those into our Q&A. You'll see a Q&A button in the upper right-hand side of your screen. There's two little talk bubbles with a question mark in there labeled Q&A. You just click on that, type your question in. I'll be able to see that. And then at the end, I can ask Chuck those questions. We'll get to as many as we can as time allots. And if we don't get to them, we'll try to email you back your answer. So for now, I'm going to turn this over to Chuck Hayes. Chuck, please take it away.
Great. Thanks, Craig. Nice introduction. There we go. About me real quick, just so you know who I am. My name is Chuck Hayes. I've been at Swagelok for 33 years. Spent about 25 or so years working in product development and in different markets, but almost the last 10 to 15 years exclusively in alternative fuel applications, including natural gas, and then that transition into hydrogen. I have a number of patents within the company, but one of the other things that I do as part of my role here at Swagelok is I'm a member of CSA, which is the Canadian Standards Association, which writes all of the gaseous standards for North America. So it basically, North America Underwriters Laboratories UL took all the electrical code or standards, and CSA took all the gas. And what's kind of funny is the Canadian Standards Association is actually located 7 miles from our offices here in Solon, Ohio. So the Canadian Standards Association is in Cleveland, Ohio. Makes sense. Well, I'm also the vice chair for hydrogen standards and our leadership committee for that, guiding all of those different standards. But with that as well, I'm an ANSI delegate to ISO TC 197 and TC 22, which is a natural gas. 197 is the overarching technical committees, overarching all the technical committees for the ISO working groups. And over the years, we've supported many different numerous vehicle platforms, development projects globally, stations, transport systems, gas injection. So we've got a lot of experience globally with hydrogen systems. So Swagelok, just if you don't know what we all do, we are global organization, but with local support. So our local sales and service centers work within the local language and the local currencies to support all of our customers worldwide. And we do have a dedicated team of clean energy specialists at each of the sales and service centers, and we work with them and do training and sharing to help raise the bar throughout the entire organization on a regular basis. We also have dedicated field engineers, technical specialists, and application engineers, and they're ones that can work one-on-one with your engineering teams to help with design challenges, product selections, reviews of systems, all the way into coming into the field and doing surveys and leak surveys, installation oversight, a lot of different services that we can offer out in the field, much more than just buying components. In fact, that's probably the last portion of our relationship as we deal with these hydrogen areas is just the state components. And we have obviously corporate clean energy market management as well. So we've got about 200 independent sales and service centers in 70 countries with over 20 manufacturing sites, and we have 5 global technical centers. And those global technical centers can do things, another thing that we can do, which is we can actually build subassemblies and areas that you may not have capacity to do. We can have those built. You can order one part number and get in something like a purge panel or a analyzer panel, fully done, fully tested, ready to hook up and put into your systems. And those can be done at our tech centers. It can also be done at most of the sales and service centers. So we have over 100 clean energy specialists in the world and 58 field engineers and application engineers that have gone through extensive training in the market. So let's talk about small molecule gas. I like to talk about hydrogen as a small molecule gas because that's really describes on what's going on with it. We have 2 different pictures here. Hydrogen ends up all over the place. It's part of our hydrocarbons. The hydrocarbons make up our modern world. And you see a couple of chains down there of different hydrocarbon molecules. And what happens is hydrogen likes to cling on to carbon molecules and makes these long chains. So you see the really long one at the bottom, which is one version of crude, and the upper one, which is a cleaner version of crude. It doesn't have a lot of impurities in it. But there's lots and lots of things that go together to make up this molecule. And that molecule, therefore, is fairly large. Hydrogen on its own is the second smallest molecule because helium is actually, you can get helium in just one atom, and it takes 2 to make H2, which is how we see hydrogen. But that atom is very, very small. A way to compare them, and I like this comparison. I don't know if it's real, but it's been shown multiple times in multiple places, but it kind of gets you the basic idea. A hydrogen atom is approximately equivalent to the size of a golf ball, as a golf ball is to the size of Earth, planet Earth. So if you start thinking about that, your brain hurts, and you figure out how small this thing really is. It's got to be really tiny because of how many golf balls I've lost, and the world hasn't changed its rotation yet. So very, very small, and that leads to some other things that come into play when you're dealing with sealing and building systems. So another big piece is who is interacting with oil and gas, and who's interacting with hydrogen. If you're in an oil and gas facility, you are going to be behind the wall, and you're going to look like there's this person on the side. He's got safety glasses and possibly a respirator and gloves and safety boots and a hard hat and hearing protection, a big yellow or orange vest, and training and a whole bunch of stickers on or things saying what they're trained for, and probably a 4-gas sensor as well. And that's who's managing and working around these chemical plants and working around these industrial gases. Well, today, you can have somebody walk up in sandals and a pair of shorts and refuel a vehicle at a refueling station at pretty high pressures. And here's an example of one gentleman filling his car, and he's standing right between a dispenser that's dispensing out at what'll eventually be 875 bar, over 12,500 PSI, into his vehicle, and it's going to start the fueling process at minus 40 degrees C and go all the way up to 85 degrees C. And this all takes place in about 3 to 5 minutes, but you're standing right between those two things. So it's a different world in what we think about in terms of safety and in terms of protecting the public. So this is one of those first places that we really bring that world of pressurized gas out. We all deal with at least here in the United States, we all have barbecues in our backyards with small propane tanks, and we deal with those where you hook them. You only do the one single hookup. You don't fill them yourself. In this case, you would be filling your car by yourself. So I can't think of many other examples of when we're managing gases or pressurized systems in our area like we're going to be doing with hydrogen, especially on cars. Okay, so let's go to oil and gas and talk about a few different things. Oil and gas systems. When we're dealing in oil and gas systems, and you look at a refinery, you see all these big pipes running around and big flange joints and so forth. Designers are usually worried about 2 things: pressure drop and velocity. So over long distances, pressure will drop in lines. It'll drop when you go around corners and you do a bunch of different things. And velocity you want to keep low because there's a thing called erosional velocity. And erosional velocity is, if you think about crude oil, and it's crude because there's crude stuff in it. It's not clean. You might have sand and all kinds of different stuff inside that flow, and that can, at high velocities, as it goes around a corner, can actually fundamentally sandblast that corner and start eroding the inside of the piping away. So you want to keep your velocities low. So the basic word is go bigger. If you ever have a doubt, make your line sizes bigger. Well, there's a problem with that. And the problem is in hydrogen, we don't really need to do that. Hydrogen velocities can go all the way up until they go sonic, in all honesty. And at sonic, we start to choke the flow. The only other time you would be careful on your velocity would be if you are getting an acoustic resonance in your piping or your tubing, that it starts to bounce and you'll see the movement. But beyond that, we can really go as fast as we need to because we are talking very high purity gas with very, very low mass. So erosional velocity doesn't really exist. And that's been seen by many of the experts in the world for years and years and years. The other problem is pressure drop. And let's talk about this real quick. When we do calculations for pressure drop and velocities and volumes and all of that, it all starts with the basics of the ideal gas law. So the ideal gas law is this, pressure and volume and number of moles, gas constant, and then temperature all come together to get us, and then we can reformulate this to get lots of different calculations. The problem is hydrogen doesn't work, is not an ideal gas. It's one of three. It's hydrogen, helium, and neon are the three non-ideal gases. So a couple of weird things about it. First of all, I mentioned propane tanks earlier. If you run a large pressure drop off of a propane tank, you'll notice ice on the outside of it. It gets cold. Hydrogen actually gets hot. That's one of the really interesting portions. That's why we start fueling vehicles at minus 40 degrees. A few of the other things are that as it compresses, the pressure, as you add pressure, it compresses and it changes how these formulas work. And I'll show you that real quick. We're not going to do a lot of math today, but I'll just give you an idea how this works. First of all, this is the ideal gas law as most people see it. However, there's a problem. There's actually another factor in there. That's the compressibility factor. Most gases are close to 1 on compressibility, so they just ignore it. But hydrogen can move into a lot of different places as it's being compressed. Okay, so let's calculate the density of hydrogen at a particular place at 27 degrees C and 700 bar. So here's that original formula. As we start running through, this is just going through the iterations for it to get down to the final density, which is rho. And the reason I bring up rho is because it's really important. And I'll show you why. Rho goes into all of our other calculations. So if we don't have our Z factor here and we're not using it, what will happen is you can have errors in all the rest of your formulas. So here are the other formulas that we get into all the time. We get into Reynolds number, we get into friction coefficients. The two M's in the middle are for volume. The top one, the delta P, is our pressure drop, and there's rho right in the middle. So if your rho number is wrong, your pressure drop calculations are going to be wrong. A couple other formulas here that are part of this whole thing. The roughnesses of your inside of your tubing or your piping are really important, and I'll show you why in a minute. So just understand that the formulas that we use get us to certain factors. Those factors are used all throughout all of our other calculations. And if you're not doing it the right way, you're going to be in trouble. So, sometimes the math looks good, but what's the real issue? Well, part of it comes into this too. The primary, the Darcy-Weisbach equation, which is used for pressure drop, is intended for liquids. And it can be used for gas if the pressure drop is less than 5% of the supply. But I just said that we're going to take something and fill up a vehicle, and we're going to go from almost empty, let's say 10 bar, up to 875 bar. That's a lot more than 5%. And then it has some assumptions. It assumes steady state, constant density, and constant cross-sectional areas. None of those are in place in most of our systems. So when we use this formula, we don't get the right answer. So what do we do? Well, we use, as good engineers, we should really be using, known calculators that are giving good results, so we're not making math errors. But a lot of the online calculators and some of the in-house Excel sheets and the unsophisticated algorithms can lead to major issues. And those major issues become the thing I said before about oversizing systems. So when you make a mistake on your pressure drop, then you're going to end up oversizing your system in the end. Going from just so an example, if you're going from a 3/4 inch to a 1-inch system, the costs can go up by about 8 times in the cost of that system. In most cases, it's not necessary. So I'll show you a few of the things. We've seen example of how this happens. We had a customer using friction factor from their regular calculator that they always use, and they use it in oil and gas, and they're using the friction factor for pipe instead of tubing. This factored into the pressure drop equation, and the system was oversized because of a math error. So the friction factor for drawn tubing is 0.0016 micrometers, and then the commercial pipe is 0.05. So they're dramatically different. So what happened with theirs? Well, they ended up calculating a 50 bar pressure drop. It was 10 times larger than what the actual pressure drop was, which was 5. When you changed over the friction factor, just by that. And what that led to was oversizing the tubing and getting really no gain for it. It is interesting, and it's interesting as you get larger and larger on valve sizes and so forth, that you increase the surface area you're trying to seal with a small molecule gas, it gets harder and harder to seal as well. So getting to larger components is not necessarily helpful. A couple things we've learned. So this is some flow and line sizing we've seen in fueling stations. So we see 350 bar systems. I'll back up for 1 second. Generally in the industry, there's 2 different pressure classes that we use. A 350 bar system, which is known as an H35. It's 35 megapascals or 350 bar. Thank you, metric system, for just adding zeros. And then there's an H70 pressure class or 700 bar. So what we see oftentimes is if we're trying to fuel at 60 to 80 grams per second, 1/4 and 3/8 inch line sizes are perfectly acceptable. On 700 bar light duty vehicles, again, 60 to 80, 3/8 to 1/2 inch max. Usually 3/8 is sufficient for the entire system. And then when we get up into 700 bar heavy duty, we see going up to 120 grams per second is typically 1/2 inch sizes. And then finally, there's a new protocol coming out soon, being 700 bar heavy duty high flow. And 1/2 and 3/4 inch lines are very sufficient to get there, to get the 300 grams per second or 10 kilograms per minute fill rates. You can do that within the 3/4 inch. We did have an example of a 1-inch system that was built because they didn't know if 3/4 was going to be sufficient, and the bogey number they were going for was 10 kilograms per minute. On the 1-inch system, it peaked at 23 kilograms per minute. So way oversized on 1-inch. But what we see all of the time right now, as people are starting to go out and design systems, especially fueling stations, and taking the experience from other industries, they're trying to push into 1-inch, and I've even seen 1.5 and 2-inch line sizing on these systems, and it's just way too big. It's not necessary. Part of the reason for that is kind of the way the clean energy market has worked in the project structure versus how typical oil and gas is. So right now, up until now, really the OEMs, the people making things like a fueling station, did all of it themselves, and the OEMs led it. So now, of course, these were small prototype projects. They were building a few of them at a time, and hadn't got into big. We don't have tons and tons of stations around the world, so we haven't got into big production yet. But the OEMs led it. So they did everything: electrolysis, compression, storage, virtual pipelines, refueling stations, fuel cells. Each one of those blocks all did everything inside their compartment. As we're getting bigger and things are starting to move, we're seeing people come off and trying to find engineering firms to go and do some of this work for them. So typically you go out and you get an EPC or an engineering company to come do it. They'll go ahead and they'll lead it. They'll lead that project, and they'll go ahead and make all the specifications. And then they send it all out to package vendors who are going to go and then build up parts of that system. A couple of issues happen there. Oftentimes, package vendors are going to buy the least expensive products they can. Could be fine in oil and gas that's moving slow and low pressures, but when you're starting to deal with high pressure, small molecule gas, there could be real issues there. High quality components are really critical. So there's just a different structure, and our Part of what we're doing now is trying to help these EPCs and making sure their specifications are done properly, specify who your suppliers are, and then solve those problems before they come down the road. So a couple of advantages. Advantages of tubing versus pipe. To begin with, I mean, we see here this big, what typical pipe looks like, the big valve on the side hanging out there. It got a big piece of pipe, got welded elbows on it, and bolted flanges and huge gate valves that are used for those. That's typical oil and gas movement. On the other side, we see an electrolyzer, and it's all using small tubing. Lots of bends in the corners, not much welding at all. Tube fittings versus flanges. You will see a couple of flanges in there, and those are on basically on exhaust lines from the discharge and the cooling system. But the actual hydrogen portion of it is all held within tubing. And you'll notice valves are small, sensors are small. It makes things easier when you're dealing with small molecule gas. Another thing is that on pipe, and the difference between tubing and pipe is, tubing is going to have a full wall thickness all the way that's used to contain pressure. It's a better strength to weight ratio. On pipe, we typically thread the ends of pipes. You do that in the field. It is far from clean to be able to do that, but the pipe has to be thicker in order to put this tapered end on it. So the pipes are usually bigger, they're thicker, they're more difficult to work with. And you can get pipe in stainless, and stainless is the preferred material over carbon steel. It does start getting much more expensive. You are paying for steel that goes into tubing or piping it's sold by the pound or bought by the pound and sold by the foot when they go ahead and draw it out. So it is much heavier, so it's much more expensive. Another thing that happens with tubing is we can do some things that you can't do with pipe. And this is things, and we oftentimes, the larger sizes, we call this small bore. And we can do things like making this 180-degree turn and do it completely with one bend, all the way around that corner. It smooths it out, reduces the pressure drop. If you don't have hard 90s, the pressure drops are lower. Same thing for this S curve on the other side. The other thing that's important is now you don't have all these threaded joints. Piping connections can be really hard to take apart sometimes. Tube fittings are much easier. So you have 2 tube fittings on the bottom one versus 6 pipe fittings. Many less leak points, and pipe threads, when done properly, can seal okay against at certain sizes for hydrogen, but really not the preferred way. We usually try to stay away from them as much as possible. So let's talk about, I just mentioned tube fittings, and as Swagelok is the founder of the 2-ferrule fitting, this is really our bread and butter, and it's designed. I want to talk about why this is the most appropriate connection style for small molecule gas. Now, again, I've mentioned before that most of the products that are being done inside of all the downstream areas of hydrogen are going to be smaller piping sizes. There can be certain applications in production, specifically steam methane reforming, that there's going to be big pipes involved, and that's just the nature of how that system works. But once you get beyond that, everything from transportation, injection into natural gas lines, on vehicle, virtual pipeline trailers to bring them to stations, all the vehicles, you're really the most appropriate fitting technology is a 2-ferrule fitting. Now, the way this works is there's 4 primary components and 2 secondary. So there's a fitting body, a front ferrule, a back ferrule, and a nut. And then there's a piece of tubing that goes in there, and then there's the operator that actually pulls them up. So all of them are critical for the proper performance. We offer training at all of our sales and service centers, and then some even more advanced training that comes out of corporate for how to be able to assemble, how to troubleshoot, and so forth. The tube fittings, and that's offered around the world in any language needed to be able to assure that this is being done properly. The other thing is that Swagelok uses standard ASTM tubing. So any tubing that meets the standard ASTM 269 standards will work within the tube fitting. That is not the case for everybody that makes tube fittings out there in the market today. So let's talk about how this works. The Swagelok tube fitting has 3 primary advantages. We talk about tube grip, gas seal performance, and vibration protection. So of course, the first thing we need in hydrogen is to talk about gas seal performance. And gas seal performance, I show this picture up front. It goes up in the upper right corner. You'll see a quarter symmetry, so a cross section on the top half of the cross section. And what you can see is everything in order. So you've got the nut, the back ferrule coming up under the front ferrule going into the body. We'll look at that a little bit closer. So on the right-hand side here, what you see is that the front ferrule is actually, it has a different angle than the body. And when the back ferrule drives under it as it's being advanced, it will lift up and slide down the inside of that body, causing a burnishing action to take place along the body, knocking out any high points that might be on either the body or the ferrule, and getting us a burnished finish to remove any what we call continuous pore structures or small gaps that would be there that the hydrogen could potentially leak through. Same thing happens on the tubing. It slides along there, pushes the tubing slightly ahead, and the tubing bulges slightly ahead of the front ferrule. And that gets us our superior gas seal performance. Gas seals are, in order to make a good gas seal, you need a long area of sealing, and that's really, really important. Single lines of contact are not good for sealing against gas. Okay, so that's your gas seal, and you'll notice that's totally taken up by those components in that single area of the design. And then the tube grip, or the pressure containment area, is handled by the back ferrule. So the back ferrule, as it drives forward, drives onto the front, and will eventually go ahead and turn and dive into the tubing. So it actually cuts into the tubing slightly. Now that ferrule actually hinges as well. Part of it still stays, so a lot of it moves plastically, but some of it stays elastic, and that acts as a spring. So it can pick up slight variations in pressure and temperature, which is good because I mentioned earlier, hydrogen can go from -40 to 85 C and 10 to 875 bar in a period of 2 to 3 minutes in filling stations in particular. But the problem is if you were to just cut into the tubing, that could give you a stress riser that would cause the vibration could cause to have it break. So what we do is we collet behind that in another section of the front, the back ferrule, that goes ahead and holds it like a collet. Like a collet goes into a drill goes into a machine center. The collets will hold it and grip firmly, and that's how we protect that area of where that tube grip was. So that's our standard fitting. That's the one that's been around for 70 some years, and has been working really well. And it's been in hydrogen the entire time, and works very, very well in small molecule gas. Now, there is another technology as we get up into the higher pressures. So a tube fitting actually does not have a pressure rating. The tube fitting is rated by the pressure rating for the tubing that goes into it. And there's only certain ranges of tubing, obviously, that can work, but we pretty much a lot of them end around 10,000 PSI or just under 700 bar, which means it's not enough to be able to do a lot of the applications we need within hydrogen. So back in about 2004, there was a push for moving to a hydrogen economy. And we started working with a number of international labs and consortiums to develop a fitting called the FK fitting. At the time, the industry thought that the pressure boundary was going to be 15,000 PSI, so 15K, so 15,000. So we called it the FK fitting. Since then, we've re-rated this fitting up to 20,000 PSI, and the industry has moved to bar. So the FK just is the name of the fitting now. It doesn't really mean anything beyond that, but that's the history behind it. It is a two-ferrule fitting. What you'll notice is that it's a male nut design. We did that because we knew that if we were going to be dealing with vehicles, there were going to be components that Swagelok wasn't going to make. We weren't going to make tank valves, and we weren't going to make a variety of other types of components that went onto vehicles. So we made this so we have the ability to license it out to others, to be able to put our port end inside of their components and reduce the number of connections inside the systems. So that's what the male end is all about. It also is a one-turn fitting. So the reason we did that is specifically because we knew automotive factories use nut running machines. Nut running machines look like a open C, and if you know anything about the Swagelok welding system, it looks just like our weld head, except a lot beefier. And those will drive down the nuts. They're a lot cheaper to buy one that goes one turn than one that has to go in angular motion for the standard, like standard tube fitting, a turn and a quarter. Those are about 7 or 8 times the cost. So we designed it as a one-turn fitting, make up by torque or make up by turns. Two other things you'll notice. You will notice that the front ferrule looks like a copperish pink color, almost red. We do that by playing with the thermal oxide layer on the part. We actually grow the clear oxide that's on the ferrule slightly, and then interferes with light as it bounces through it. Turns it into a prism. So it turns out a reddish color. What's funny, back in 2005, it was always the same color, but nowadays you could take it into 5 different rooms and it can be 5 different colors because of LED lights. They change the wavelengths of the light, and it changes the color and the way it looks. Sometimes it looks brown, sometimes it looks red or pink, it's kind of interesting. The important thing is it doesn't look bright silver. That was the point. We did not want it to be able to be interchanged accidentally in a plant that was using 2 different Swagelok ferrule designs. You could definitely see that they were different. And then the last piece is you'll notice that the whole thing is on an arbor. That arbor is assembled here in our factory to be able to allow the operator to be able to slide the nut back slightly, make sure the rear ferrule is in place and in the right orientation, and then you screw it into the body where it's going to be assembled. And once it gets in, that angle on the front of the arbor will close down, and you can slide it right out. The reason is we found that one of the biggest errors that happens, remember I told you about the 4th and 5th elements inside of a tube fitting? The 5th one being the operator. Traditionally, when you get people putting together tube fittings, many of the installers, the first thing they do is take them apart, which is kind of concerning for us because we spend a lot of time and money to make sure that everything is in the right orientation and in the right part every time. And any tube fitting from Swagelok you can take out of the box, stick in a piece of tubing, and mark that tubing for depth, put the tubing in, pull it up the appropriate amount of turns, and you're done. That's it. Because we already know everything is there and in the right order. And we do that through a variety of controls within our factories. The problem is other companies don't do that, so the installers are always worried that things aren't in the right place. Well, the problem is if you miss a back ferrule, or if you flip it upside down, or put them in the wrong order, then bad things happen, especially with high pressures and small molecule gas. So this way we were able to assure that it's always right when it gets out in the field. So lots of things done specifically for hydrogen, specifically looking at the potential of going into a potential automotive type factory. So I'll show you this. This is a model. This is again in that quarter symmetry I mentioned earlier. It's an FEA model, so fine element analysis done for how to develop this. This was one of the first fittings developed using FEA back in the early 2000s. The computers were this was equivalent to a military computer that we were using for it, and it could do about 40 runs of design over a weekend. Today we do that while you walk down and get a cup of coffee on the newer computers. They're so much faster. But as you watch this, it moves kind of quick. You'll see with the back ferrule driving under the front ferrule driving forward. I'll play it multiple times. What you see there is you see stresses coming and different colors. Think of them like weather radar. So the darker the color, the more stresses that are being built up. You'll see the back ferrule drive under the front, lifts up the front ferrule, and it slides along the body, and then it slides along the tube. But wait a second, it's doing something different. It's actually diving into the tube as well. What we found was in order to get the higher pressures, we have to use a different type of tubing, and it's called eighth hard tubing. Eighth hard tubing is different in multiple ways from instrument tubing. One of them is they don't control the OD of the tubing as well. Often because it's used for things called cone and thread fittings. We'll show you that in a minute. And in those, you're machining it, and the outside doesn't matter. So since we couldn't be sure that the outside of the tubing was going to be in pretty good shape, we actually create our own seat along the tubing to make sure that we seal well. The back ferrule, you'll notice, is much beefier than the standard tube fitting, and it has to be because of the pressures. So, but it still has a collating area in it. The dive is much more aggressive to be able to hold, and the basic functions are all the same. How the fronts and backs work. You'll notice on the outside of it, there's this long nose. We affectionately call it the diving board, and it comes down and hits the body. And there's a 45-degree angle there. That gives you your torque spike when you go ahead and you make up the part. Because of the angle, it allows you to advance it slightly every time you remake. That allows 25 remakes of any assembly in any body. So I mentioned another type of connection. This is cone and thread. Full disclosure, we make cone and thread. We'd be happy to sell you cone and thread as well, but I'd be happy to tell you why not. It's not the best thing for hydrogen. In oil and gas, this is considered to be the go-to standard for medium pressure. Medium pressure is anything over 10,000 PSI. It has been, now here's the beauty of it. It's been around for a while. It was developed, depending on which story you believe, either in 1890 or in about 1910. So this is 19th century technology being used in the highest technology stuff we're using today. It is got some problems. So first of all, let's look at the body. One side's disassembled, the other side's assembled. The body has a chamfer in it that it's threaded for the gland to come in. So basically what you do is you take a piece of tubing. Remember I said the OD didn't matter. It didn't matter because you're going to cut a cone onto the end of the tube. Then you're going to put a left-handed thread on it. So you have to machine that. And then what happens, you slide the gland on, then you slide on then you screw on the collar. The collar holds on by the threads, and the gland pushes against the collar, as you see on the assembled side, and that all pushes the cone into the body. Okay. Now, a couple of problems. The first one is if the threading isn't done properly, you can strip out that thread on either the collar or on the gland under the pressures that we're at. You'll notice on the gland there's only about 2.5 or only about 3 threads of engagement, full threads of engagement on that, which is what's required to get your full strength in a thread. So if you screwed that collar on a little bit further back, that gland may not be on enough, and that can blow out. There's other ways the left-handed thread can get screwed up when you build it. Most of this is done either by hand or on very small machines, so they're not very precise. The other thing is that the angles are really critical. At Swagelok, we use our differential angles. Our cones, we specify 59 degrees and 60 degrees on the taper. So they're very, very close. So there may actually be some areas that can burnish slightly to give us a longer seal area. But there are companies out there that actually sell a 57-degree cone and a 63-degree body. What that means, and they actually tout it as something positive. So that means you get a solid, highly loaded single line of contact. But single line of contact is not a good way to seal against a small molecule gas. It's fraught with problems. The other thing is you end up coining in the surface of that seal. So if you ever try to take it apart, put it back together, you've got to rematch up right where it had coined in the first place, all the hills and valleys, which they usually don't, which is why when these leak, and they leak, people go and nip them up. They pull them up tighter, and they're basically reseating the whole fitting every time they do that. One interesting piece about the entire design, if you notice that little hole in the top coming in perpendicular, that's a leak port, and they put that in because they leak. They leak in oil and gas. They leak with small molecule gas. They are really prone to vibration and any kind of side loading on the system because, as you notice, that cone goes into that chamfer and has nothing ahead of the sealing point to control any kind of angular displacement that's being placed on the system. So what we've seen is we've actually seen in places where these things are out there where they leak for a while, or they leak. They go in to depressurize the system, go in to check it, and it reseals itself. And the reason is that side load has been taken off, or whatever was there, however it was there from when the system was running. So the best way to see this is if you go to an oil and gas facility where there's a whole panel of these on a wall, you look under the panel, and there's always going to be pig mats. Those are the mats that we put under to collect oil. They're under every single one of these things because they're dripping oil. Now, a drip of oil is not very much volume, but that would be a heck of a lot of volume of hydrogen. So not recommended for using this as a standard component in hydrogen. We see lots of problems all over. But if you'd like them, we would be happy to sell you ones that are better than everyone else's in our in our system. So so a couple things on system levels. Really proper selection of components. So we just talked about fittings and the difference between high quality tube fittings and modern designs and then old world designs of cone and thread, and why it's really important. People have also tried to do flanges all the way down to 1/2 inch, and the flange design is a huge surface area, relying on a gasket being compressed, relying on materials of that gasket not to permeate all the time. Not a great design for high pressure areas. Really, your best approach for that fittings is tube fittings. Valves need to be careful with. Ball valves are we've got ball valves that work really well in hydrogen, but some people are leery about ball valves. In these systems, because of opening that large pressure differential across them, number one, and number two, if something happens to them, you can't tell what the orientation of it is if something were to break in a stem, let's say. We are working on new versions of valves to work really, really well over long periods of time with some advancements as we're working into the small molecule gas. And those will be coming in the near future. Really, when you're looking at valves, needle valves are the way to go. So needle valves can be actuated. They can be manual. They still have a life because you're going to go metal on metal. There's no elastomers involved in the seal. The problem is, and what we've seen is some of these 1-inch valves that I mentioned earlier had absolutely massive air actuators on them. They were the size of a small garbage can, and they were putting so much load onto those poor little needles that they were getting very, very low cycle lives, 15, 20 cycles before they would wear out and break. They would just deform the material so bad in order to make a seal. So again, getting up into the larger sizes can lead to problems of getting valves to seal. The really, really important thing about hydrogen systems is, by standard and by the CSA standards for infrastructure and vehicles, you have to consider every joint to have a 10 standard cc's per hour leak rate. Well, what does that mean? That means when you do calculations for safety, if this is in an enclosure, you add them all up, you figure out how much 10 cc's per hour would be and how much that would be volumetrically inside of your enclosure, and you're not able to go over a 1% threshold of hydrogen in air for safety reasons. So the lower flammability limit is 4%. The safety limit is 1%, and that's what it's used for, is calculating. The elimination of unnecessary components is really, really important. I'm talking about double black and bleeds in a second here, but one other thing is properly venting the systems. So while when hydrogen comes in contact with oxygen, can create a flame. There's designs for the for venting being, for example, it needs to be 3 meters above any surface, or 10 or at least 10 feet off the ground. So if there was a flame in a vent system, it's not shooting in somebody's face or catching any surface on fire. But the one issue is, in many cases, one of the devices we have on hydrogen systems is thermal pressure relief devices designed to go and to release the pressure if there's a thermal event. So you want to empty that system as quick as possible because storage tanks can't handle that, what's going to end up being a large pressure rise coming from a thermal event near it. So you want to vent quickly. So no flame arresters in those systems, and be careful to make sure those are sized properly. You need leak monitoring on site. So leak monitors are used a couple different ways. One of them is using the potential for ultrasonic, but it doesn't usually work really good in loud facilities if you've got other things going on. But you can have ultrasonic, you can have sniffers that are actually smelling for the hydrogen, and then flame cameras, and you actually interlace all of those in systems. And there's companies out there that design those. Draeger is one of the great ones out of Germany that can teach how to do the entire system. Proper spark protection is important. Using ATEX and or intrinsic safety for in the US and process safety concerns, one thing to pay attention to is lightning protection. I've seen stations going in that do not have lightning protection, and that can be a problem if you start getting static buildup. You want to have at least one lightning protection in all of them. And a lot of these are all defined within NFPA 2. So National Fire Protection Act, number 2 is for hydrogen systems and the installs. So let's talk quickly about double block and bleeds. We'll get to double block bleeds in a second. So we're picking the right components. Like I said before, flanged valves and gate valves and butterfly valves and these big relief valves that we see in oil and gas. Really, we're looking at instrument style valves, ball valves, and needle valves are really much more what we see within the hydrogen world. So we're picking the right components. Let's talk about that double block and bleed. So double block and bleed, if you're not familiar with it, is usually a place where you can block, like let's just say this pressure gauge that's here. You can block off the pressure gauge, block off the line that has the pressure coming from the process vessel on the other side, and then bleed out that pressure, and then now your pressure gauge, open up that valve to the pressure gauge, and now there's no pressure at the gauge if you have to replace it. Okay, great. This is used all over the place in oil and gas. Why? Because the processes don't shut off. So if you have to do maintenance, you need to be able to safely go in and maintain that system while the pressure is still in the lines. In almost every case in your hydrogen system, there's a problem. If you crack into the system, you're going to let air in, and air has oxygen in it. and that's a problem. So what you need to do is after you've done maintenance is you need to go ahead and nitrogen purge that system down before you reintroduce hydrogen. So the recommendation is you shut the whole system down, bleed down the hydrogen, then go ahead and do the work and then refill it. So if you're having to do it in that way, you don't need double block and bleed systems in all over the place inside of your hydrogen area. Very few cases that you would need it. And it's just adding a lot of connection points that go into your leak budget, and any reduction of connection points. Kind of sounds funny from somebody in a company who's selling fittings and valves that we want to sell you as few as possible, but that's the best design, the safest design inside of hydrogen. So again, here's the whole concept of why you're going to be venting and so forth, and venting out that entire system. Which brings up one other point, that when you're designing a hydrogen system, you're going to need a nitrogen purge system on it as well. So when you do that, we do have products that are already pre-done and pre-built, come fully assembled as a single part number for being able to do bottle changeover and do those purging systems really well for you. And your field engineers and sales folks can help you pick those as you're doing your design. And why is it? Why so much purging? Well, basically, hydrogen plus oxygen equals rocket fuel. That's it. And when you put them both together, they can spontaneously ignite and create a flame. So always watch out about the mixing of hydrogen and oxygen at the same time, unless you want to go back to the moon. Okay, so conclusions. Tubing systems are great. They work really well for leak type performance and small and smooth bores, reduction of friction on those, reduction of pressure drop. Tube fittings are really the best seal for small molecule gas. Swagelok makes the ideal tube fitting for that. And then don't supersize your systems based on oil and gas calculations. So use the right calculations, make sure you've got the right calculators if you're using them. Make sure you're dealing with the compressibility factors, and know that your pressure drop is going to be different depending on what the density is at different points within that system and different times that you're charged and uncharged inside your systems. Hydrogen can be handled really well. We've been doing it for years and years and years. The people that have been doing it are pretty much specialists. And now as we go out into the bigger world, it's things like this that are going to help start educating everyone on different designs. So that was my presentation for today. And I guess we'll see if we have any questions. What do you think, Craig? Got any questions out there?
Great. Thanks, Chuck. It was an excellent presentation today. We do have time for a couple questions here before we end. Again, if you have a question, please use the Q&A button that's kind of in the upper right-hand side of your screen. It looks like two little chat bubbles with the question in it. And type your question in. We'll be able to see it and go from there. We've already gotten a couple questions, Chuck. So if you don't mind, I'll just throw a few your way. And the first one's a little bit of a clarifying question, something you had mentioned earlier. 316 stainless steel is a preferred material in hydrogen applications, especially. Mm-hmm. And a lot of that, I believe you said, is because of hydrogen embrittlement. So just a clarifying question there to make sure that's okay. And then if so, how do designers protect or kind of defend a little bit more against embrittlement with their systems?
So your best way is the 316 family. One of the simplest parts about it is that under the ASTM standards that make up that material, you can have a variety of percentages of different components inside of it. Nickel is one of those primary ones. Nickel actually stabilizes the austenitic structure and the crystalline structure inside the steel. And ASTM says you can have between 10 and 14%. When we look at the loss of ductility, which is one of the things, is you go from ductile being bendable and easy to manipulate, to very brittle on the other end. As you lose ductility, as the nitrogen levels drop, there's a graph that actually shows it drop off a cliff at 12%. So 12%, the loss of ductility is really, really severe. So we recommend staying in 12% and above nickel equivalencies for all valves and fittings. 11% is fine for tubing because tubing doesn't have the same type of stress risers in it. But all of our Swagelok materials for everything done in hydrogen are all done at 12% nickel. And then we also have an elevated chrome because chrome can helps prevent against corrosion. Corrosion can lead to anomalies in the surface that the hydrogen can then attack. Same thing with cracks. So high quality components, high quality materials are really, really important.
Okay, great. And as you were kind of answering that, somebody just popped in with a question that says, can you please restate what tubing standards the fittings work with?
Yeah, it's ASTM 269 for standard tube fittings. I am blanking on the 8th hard tubing, but we have that information in our tube data sheets for our tubings. The FK tubing up until half-inch sizes, the FK tubing is a special spec that we use. It goes to an ASTM standard, but it's actually a Swagelok specification for it because of the issues of cone and thread. Above the 3/4 inch and 1 inch can actually use cone and thread as well. So cone and thread tubing is out there in the world as well. But we can definitely get you those numbers.
Okay, great. Another question, and I wasn't sure that you covered this one, but do you have any comment on the use of tube fittings in cryogenic hydrogen, either as a gas or in a liquid phase?
So we are working diligently on that. So here's what I can say. The materials will be fine. We already know that. So cryogenic hydrogen is minus 253 degrees C or 10 degrees Kelvin. The only thing colder is outer space and liquid helium. So in liquid, if we're talking liquid, and that's liquid hydrogen gets to that level. We have customers that use it on a regular basis. We are working to get letters of certification for hydrogen for our fittings at those temperatures. There is a slight problem, which is there is a required test in the ASME code that requires what's called a Sharpie impact test. The problem with the Sharpie impact test is when you hit something, the concept is if you hit something that's really, really brittle with a sharp point, it's going to crack. Think about hitting a block of ice with an ice pick. Same concept. Well, the problem is when you hit it, it heats up. So the temperature changes. So the Sharpie impact test just says you can't use it below 176 degrees C. So you can't do the test to qualify the materials. We've been trying to work through this and understanding a clarification from the bodies. We're also working on getting additional letters and or test results for all of the fittings at those temperatures. Are they being used? Yes. Do they work? Yes. Can I prove that in any way beyond saying somebody told me so? No, at this moment I cannot. But there's very few labs in the world that can actually do any of that testing. I think there are now 2. There was 1, and we're working on getting closer to that.
Great, thank you. The next question, again, reminder: if you have a question, you can use the Q&A button that's in the upper right-hand side of the screen and just type it in. We'll catch it. You had mentioned, I think, earlier in the presentation about online calculators and how that kind of leads to oversizing and things like that. Do you have any recommendations? One of the listeners has a question about that. Do you have any recommendations on pressure loss calculation tools, whether online or someplace else? Is there anything you would recommend folks use for pressure loss calculation?
We use Arrow. I am not in the area that does that. However, it offers you about 7 or 8 different algorithms to be able to do it. You have to do some research into the algorithms to make sure it's properly using the Z formula for compressibility, and the algorithms will tell you which ones they're using. That's your best bet for that. There is one other possibility, which is NREL, which is the National Renewable Energy Labs out in Boulder, Colorado. Part of the Department of Energy has done and developed for stations a complete set of software that you can basically drop components into, and it'll do all your calculations for you, that meets all of those calculations. I do not know if you can do other systems with it outside of dispensing systems and cascades. But you can go to their website and download that software and play with it if your IT people will let you, which ours won't. So I have not physically played with it. I know others within our organization have on personal computers, but that's another place to go. And it's just watching really carefully. If you were to Google a calculator for pressure drop, you're probably not getting the right formulas.
Okay, that's good information. No, thank you very much. Well, folks, that's all the time that we had today with Chuck. Chuck, thank you again for sharing a lot of your knowledge on hydrogen fluid system design and differences with oil and gas. If you guys have any other questions, please feel free to reach out to your local SwageLock Sales and Service Center. They'll be happy to take your question and help get you an answer and get you taken care of. We thank you today for your time and spending some time with us, and have a great rest of your day.